Great. Good morning. I hope you had a nice evening. It's as I said yesterday, for us it's a major challenge here to introduce a number of topics that are considered quite complex. But based on especially to the questions that you have asked yesterday to our keynote speakers, I think that the level of the audience is quite high. So let's take this chance and take the challenge and see what we can really learn from this process, from your side, but also from our side, because also for us it's an experiment. It's an experiment where we would like to demonstrate how, when we expose students to quite complex topics, we believe that we are supporting significantly the development of key skills. So I will try to, in my presentation for the next hour, I will try to introduce the different topics related to the effort we are making to come as close as we can to Big Bang, to the start, let's say, to the birth of the universe. And as we are here in Thessaloniki, in the capital of Macedonia, I thought that we have to pay some tribute to Democritus, who lived and worked not very far from here, about 150-200 kilometers in Avdira, in Thrace. And he was the first who introduced the idea of atom. And he had really this concept that everything consists of atoms and empty space. So in my presentation, I will try to convince you that the empty space has much power. In fact, it has more energy than the space as we know it, and the matter. So I will try to introduce a discussion, because I would like to have this interaction with you. So I would like to ask you what these two pictures are presenting. Yes, please. Yes, you. Yes, you. It's a supernova. Do you know what a supernova is? Great. So, as it was presented in one of the keynotes yesterday, the star is a nuclear machine, and it produces nuclear energy. On the other side, the gravity is pushing everything to the center. So, when the fuel is consumed and the star is approaching the end of its life, because of gravity, is going to collapse. And if the star is big, much bigger than our sun, it collapses in such a way, with this big explosion that is called supernova. There are two pictures in the screen. There is, this is the first one, and here is the second one. Can you tell me what is the timing? Which is the taken first, according to your view? Yes? This is first, and this is second, you think? Okay, and how we have managed to do that? Okay, so what, in principle, this event was observed in February 1987 from Australia. although it was February, it was a very nice summer night in Australia at the southern hemisphere. So the telescopes were observing the night sky, and they have seen this this unique event. So as they didn't have any idea when this event is going to happen, then they went back to their archive and they found the star that was exploded. Okay? So this is first, and this is second. There are many more things. I mean, we can spend the whole hour of this lecture discussing about this picture. So another very important aspect here. This explosion took place at the Large Magellanic Cloud. It's a companion, a small, let's say, satellite galaxy of our galaxy. It is located at about 160,000 light years away. Is everybody okay with the term light year? I know that there are some let's say, students from the first class of gymnasium. Is everybody familiar with the term light year? Are you okay that I'm measuring the distance in light years? Everybody? Okay. So that means that when the first humans were walking on the planet, this star exploded. And the light was traveling for 160,000 years to reach our planet. Okay? So when we are looking the sky, what we see? A picture of past. Okay? Even when we are looking our sun, the picture is 8 minutes old. So we see the sun as it was 8 minutes ago, not now. Okay? So when we see the sky, we see the past. And by looking the past, we are trying to understand how the universe is developing, how it is evolving. And based on that, we are making numerous observations of, for example, similar stars like ours, and that's why we know our future. Okay? But we as humans, because humans want to know everything, how far do you think we have to reach? How far we would like to see in order to know everything? How far we have to travel in the past? 14 billion years. So we would like to see the start of everything. We would like to see the Big Bang. And this is the major research issue this moment, to reach the Big Bang. During the summer school and during also the other lectures, we will present to you, in principle, 4 topics that are related with 4 Nobel Prizes that were awarded the last 15 years. The first one of them, this was awarded in 2011. It was a study that by studying this kind of remnants, this kind of dead stars, the supernova remnants, we are able to see that universe is expanding by a bigger and bigger speed. So it's accelerating. And it is not we are not able to understand why the universe, after almost 14 billion years, keep expanding in such a high speed that is also increasing. So experimentally, this was a theoretical issue, but experimentally, this was proven back in 2011. And the Nobel Prize was awarded for this purpose to 3 American researchers who, by studying this supernova, they managed to provide evidence, experimental evidence, that the universe is expanding in an accelerating mode. And how we are doing that? We are making images of the deep sky, because this supernova was just in our neighborhood. It was very, very close. But we would like to see supernovas that are located very far away, to other galaxies in the deep sky. So how we are doing this? This is the process. We making pictures of the deep sky, and we are taking images like this one. These are galaxies here. These are galaxies. And we are measuring the amount of light that exists on each photo. And suddenly we see that in this photo there is more light. And we assume that this light is coming because of such an explosion, such a big explosion. So we believe that in this galaxy here, there is a supernova. So we are collecting data, and we are just removing the background. So here, this picture is the outcome of removing, let's say, from this picture, the background. So then we are able to see the supernova. In fact, this is a very similar event like this one. But this is much further away. And by studying these supernovas, we are able to see this accelerating process in the universe. And other examples. Here, this is it's much closer, so we can have a clear view of the supernova that exploded at the limit of this galaxy. So this is the difference image, and this is again a supernova. So in the same process, in the effort astronomy, conventional astronomy is doing, of course we had to improve the instruments, we had to install, let's say, telescopes high on the mountains in order to have a clear view. Again, the atmosphere was creating problems, so we have sent the telescopes to space. We have much more advanced telescopes, Hubble, James Webb now, and we are able to see further and further away, approaching the Big Bang. And it's very interesting because about 2 years ago, thanks to the technology, but also to nature, we were able to make an image of a star that it is located very, very far away. In principle, we will not be able to see the star. But because of a natural effect, we were able to see it clearly. So this star, Earendel means the first light. This is the name that was given. Exists about 900 million years after the Big Bang. Okay, it's a period immediately after the Dark Ages, as we will discuss in a few moments. And we were able to see it because of gravitational lensing. So this is the picture here. Again, a picture from the deep sky. And here we can see a line, a red line in principle. This is because these galaxies that they are here are bending the time-space. And because of this bending, they are creating a gravitational lens, a magnifying lens. Imagine that in this picture, we have in this point a magnifying lens. And there, at the edge of the lens, we are able to see this star. So it's, of course, the significant improvement of technology with the unique James Webb telescope, but also it's a matter of luck that this star was at the exact position in order to be magnified about 4,000 times in order to be able to see it there at the limit of the magnifying lens. So this star is very far away. Okay, so this is the process of gravitational lensing. And here, by the way, the slides of the presentation includes numerous links and so on. All of them will be available to you on the website, so you can click all the links and collect all the information that you have. Here, it demonstrates the effort that we have made to locate stars that are far away. I mean, in this effort of conventional astronomy. But let's say with conventional astronomy, we are finally approaching a closed door. And this door is this, let's say, soup, cosmic soup, as it was presented yesterday in the keynote talks, where we are not able. So here the universe is not yet transparent, and we cannot use light to see behind this limit. So our efforts stop at about 380,000 years after the Big Bang. And just to understand, let's say, these numbers, because we are using these numbers and sometimes, okay, they are impressive, but it's important to understand the overall view. I mean, what this graph demonstrates, it's part of a balloon. The universe is growing. We are, let's say, currently located here in a very thin line at the end. This is the present. And here is all the past of the universe. It's 13.77 billion years. So just to understand the limits of that, let's suppose that we will transform this for a moment to 1 year duration, okay? Let's suppose that about this time interval is about 1 month. So we have 12 months. Here is the first second of the first day of January. And here we are on the 31st, the last second of 31st of December of the year. When do you think Earth was created? In which month? 25th of December. Please remember, yesterday there was a discussion that the Earth is about 5 billion years. 5 billion years old. 5 billion years. So in principle, I have to move about 5 months. So Earth is created at the end of August. Earth is created and the solar system is created at the end of August in 12 months duration. The dinosaurs are walking on the planet during Christmas, 25th of December, okay? And the humans start walking on Earth after the 23:54 of the 31st of December. So we have about six minutes of life in the framework of the universe evolution. Okay? Is it clear? Sure? So, this star, the star that we found, is about here. The star is about here. Maybe I can take this one. Okay. So, the star Eridel is about here. So, the universe was very hot. It was like I have a big can and the soup is very hot inside. And suddenly, I'm throwing everything on the floor, and as it's expanding, it's becoming colder. And then it's becoming transparent. And then we can see. Okay? And it takes some time, we call them dark ages, till the formation of the first stars. The first galaxies, and so on. And then it's expanding. Look at this point here. This is the acceleration that I was talking about. So it's becoming faster. In the beginning, we said it expanded very fast. Then it became, let's say, to a constant speed, and now is accelerating again. And this is what we said yesterday. We have no idea why this is happening. So our effort from here, from this point, from these 6 minutes of life of the evolution of our civilization, we want to see back here. Okay? It's a major challenge. It's a major challenge. And I believe that this is going to be the challenge also for some of you who want to follow, let's say, a scientific career in the field. So the conventional astronomy cannot work. We have 3 different ways to approach this issue, to see in this cosmic soup. Okay? Because it's very crucial here. It's very crucial to understand all these points, because this is the key to understand how the universe is possible to expand continuously with an accelerating speed. As it was discussed yesterday, everything we see, the stars around us, everything, consists of matter, that it is about 5% of the total energy that was released with the Big Bang. About 25% is the dark matter. It behaves like matter, but we don't know which particle is associated with. We understand, as you heard yesterday, that because of the rotation of the galaxies, the rotation speed of the galaxies, it must be additional mass in their structure that we are not able to see. So we have experimental evidence of dark matter, but we have not managed yet to identify the particle that is really responsible for carrying it. And there is about 70% that is causing this expansion, accelerating expansion of the universe, for which we don't have any idea. In principle, it looks like when the distances between the stars, between the objects, is becoming very big, the gravitational force has the opposite impact. So it's pushing the masses away. So the power of empty space is more significant than the power of matter. This is the graph that was presented also yesterday with more accurate results and data that we are getting from different experiments. So let's make a small video break, let's say, to see the picture of our universe. This video was created back in 1977 from IBM, and we really prefer to show this video because it presents the evolution also of the scientific inquiry. I think, again, we have some problem here with the... Okay.
picnic near the lakeside in Chicago is the start of a lazy afternoon.
We will see a couple having picnic
we begin with
next to the Chicago lake.
Wide, which we view from just 1
and
meter
every
away.
10 seconds,
now every 10 seconds we will look from
the
10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters, the distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move.
During the presentation, I will come again and again to the issue of empty space. Look this picture as it is developing. The Earth in there and the empty space around it. So
now
this is the
path
of the Earth moving around the Sun.
The neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper.
Now the stars in the background start moving.
Stars
so the distances are so big that we can see
galaxy.
A bigger structure, which is our galaxy.
Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1 million light years.
Now what we see are galaxies,
bring a new level of structure
if
to
they
the
are
scene.
not stars anymore.
Glowing points are no longer single stars, but whole galaxies of stars seen as one.
We will see some galaxy clusters, like the one that deviate the light in order to be able to see this star that was located so far away.
This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal.
This is the
richness of our own neighborhood is the exception.
The picture of the universe as
the
we
trip
have
back
it.
to the picnic on the lakefront.
Now we will do the opposite. We will go very fast by dividing the window every time.
In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative
So
inactivity.
from very large scales, we will go to nanoscales.
A proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom.
We are entering now to the sea of the electrons that are around the nucleus, and we are getting a quite similar picture. Again, empty space. The atom is in principle empty,
now we come upon the 2
space.
inner electrons held in a tighter swarm.
And there in the center,
as we draw toward the atom's attracting center, we enter upon a vast inner space.
We are locating the nucleus.
At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
So, is it possible really to study the first moments after the Big Bang by looking to the microcosmos? Maybe yes.
You can see the stars, but they were all of years before. And you can see how much time does the universe made.
In principle, we are developing technology to cover all these areas, let's say, from galaxies till the basic structure. Because in the first moment, if we want, let's say, the first approach to see the Big Bang is in principle not to see it directly, but create the conditions immediately after the Big Bang. And in order to do that, we have to give to the particles so big energy in order to see, let's say, their components, what they are consist of. And to do that, we are using accelerators. We have to give to the particles the very big energy they had the first seconds after the Big Bang. This is how we are trying to approach this issue. And it seems for the moment to be the most successful approach. How we can do that? Now we are not using telescopes, but we are using accelerators. We are moving 150 meters under the ground, and we are installing a very big experiment, a very big, I would say, particle highway. It's about 27 kilometers long, and we are using it to accelerate particles, to reach very high speeds, to reach very high energy, and in this way simulate how the particles were colliding in this cosmic soup. After the first seconds after the Big Bang. And this is what we are doing. This is the most complex human machine. I don't know if you had the opportunity to visit. Usually schools are organizing visits to CERN, and students have the chance to visit this infrastructure. So we will see how difficult in principle is to give such big energy to the particles. And we have this complex system to do that. Let's see another video here to introduce the issue. So everything starts from the atoms of hydrogen. We have to remove the electron, and we will accelerate protons.
Culminating in CERN's spectacular Large Hadron Collider.
It's very difficult to create a linear accelerator. It has to start from Moscow and go to LA in order to manage to get such high speed. So we are going to use rings. And every time the particles are making a cycle, we are giving them an energy kick. And they are increasing their speed. Let's see how this is happening. So these are protons. These are protons. Accelerated
this initial acceleration has caused Lina 2 to be likened to the lumbering first stage of a huge
in the first
rocket.
Step of the process that is taking place at CERN.
It'll be traveling at 1/3 the speed of light.
So at this point, they have 30%, 33% of the speed of light.
In order to maximize the
we would like to approach
the packet is divided up into 4, one for each of the booster's rings.
So we cannot accelerate them immediately, so we have to go step by step as we are going in the car, and we are setting the first speed, the second speed, third speed, and so on. So we are creating these packages, these bunches as we call them, of particles, and we are accelerating them.
Magnets exert a force on the passing protons.
The magnetic field is crucial here to keep the particles
so powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6
we can reach a limit. We are not able to give more speed because then they are going to hit the wall and we will lose everything. So we have to move to a bigger ring.
It's then flung on into the proton synchrotron, by analogy, stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 meters in circumference.
The blue is just because we are going to separate the particles, protons moving to the opposite direction in the highway later. So it's still protons, but we are using the 2 different colors to demonstrate that we will separate them later.
Field cannot translate into increased velocity, as
so
they
are already at some point that they cannot increase their velocity anymore.
The added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier.
They're becoming
the microscopic kinetic energy of each proton is measured in units called electron volts.
When we started, it was like having a small lamp moving it around. Now we have a whole
the protons are now 25 times heavier than they are at rest.
Heavy. Now,
the packets of protons are now channeled into stage 4.
In principle, what we would like to do is we would like to bring the particles in the conditions
to accept protons
as they were the first moments after the Big Bang, and to create these collisions.
Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large
So now it's time to enter this particle highway to the Large Hadron Collider.
And straddles both France and Switzerland. Lying deep underground, it has a circumference of 27
kilometers circumference with the speed of light. how many times they are making their cycle in 1 second. There is 1 missing, 1 0 missing. Yeah. So, you want to say something? $12,000 times. Bravo, Fivo. Bravo. Πολύ ωραία. 12,000 times per second. 12,000 times per second. And we are doing something that we wouldn't be allowed to do in a highway where the cars are moving. We are creating 4 junctions, 4 points that we are going to... Oh, I lost the sound.
Clockwise. The counter-rotating beams cross over in the 4 detector caverns, so where they can be made to collide.
We are pushing them to collide. The tube has this size,
and it's the debris from these
and it's full of protons.
Trapped in the
full
detectors.
Of protons. Still, most of the protons are going to cross each other without understanding the existence of the others.
Packets.
Because again, we
During
have
this time,
a complete
the LHC adds extra
here.
Energy to each proton,
Still,
whose
we will
velocity
manage
is now
to have
so
some
near the
collisions.
speed of light that it goes round
And
the 27-kilometer ring over 11,000
with the
times
necessary
each
equipment
second,
to make a photo
at each revolution
of this collision,
from the pulsed electric field.
to monitor this collision, because this is
Finally,
where we are going to get the data.
Has an energy of 7 tera-electron volts, and they're 7,000 times heavier than at
electron
rest.
volts is the energy that they are getting. And as they are colliding to the opposite direction, it means that we have a collision of 14 tera-electron volts. This was also the idea of having the particles moving to the opposite direction, to increase the energy of the collision. Because the higher the energy, the closer we are at the energies of Big Bang.
To a collision course.
So this is the idea. Here are the protons, we see the quarks inside, and in principle we have the quarks, the components of the protons collide with each other. And this is the device that we have, an advanced digital camera, I would say.
And it's hoped these
quite big, 30 meters high, 30 meters in diameter. So to get information on how our universe was created.
In the future.
So this is the first technique that we have. And let me ask you a question. Let's suppose that I have 2 strawberries, 2 small strawberries. And I'm bringing them in collision. I'm giving them enough speed. Let's suppose that I have a collider where is increasing the speed of the strawberries. Is it possible to create a watermelon from their collision? 2 small strawberries, mass M and mass L. I'm creating one particle. Could it be the mass of this particle bigger than 2M?
So it could happen.
It could happen. How many believe that the mass of the resulting particle could be bigger than 2M? All the others believe that it is not possible. I will need to repeat my presentation, Mr. Bourdias. So I can create a very big watermelon because the small strawberry has increased its mass, as we said. because it's moving very fast, okay? It has become, as we said, an energetic elephant. So two elephants are colliding. And this is the idea. This is how particles are created. From small ones, very high energy, very big speed, they collide and they create a watermelon that is moving not so fast, a slow watermelon. Okay, this is the idea of the colliders. So in principle, this is a nice drawing. By the way, this was from the school book of the 3rd class of Lyceum, 17 years old students in Greece. The previous book that included this issue, and I believe it has important value to demonstrate this idea. Okay, this is the machine. You see also the side at CERN. We are trying to identify the particles. It's split like an onion in different parts in order to be able to understand, let's say, okay, here I have a track of a particle, then it interacts here with electromagnetic calorimeter, so it is a photon or an electron or a positron. If it goes through, it's a muon and all the other particles. And in this way, I'm identifying all the particles I know. And if there is something that I don't know, there are two scenarios. Either I have made a mistake, or I have found a new particle. This is the real picture, and you can see also the person here. By the way, this facility you can visit at CERN, and you can go down, especially during December and January when it is open, and it is very, very impressive. So this was the way to identify the Higgs boson. This is the second Nobel Prize that we are going to discuss in this summer school in about 10 years, 11 years ago, okay? And this is the creation here in the center. This is a picture of taken from this digital camera. Here in the center, a Higgs boson was created, and its signature are these 4 muons, because the Higgs boson, that it is responsible for the mass of the particles, is not living so much. We are not able to detect it, but we can see its signature. So when it dies, it creates 4 muons. Is one of the way that is going to die. And by detecting these 4 muons, we are able to see that here, during the collision of the protons, a Higgs boson was created. And this was, let's say, the second Nobel Prize rewarded back in 2013 for the discovery of Higgs boson. The announcement took place on the 4th of July 2012, and we were very lucky because we had a similar summer school like this one. This was for Greek students in Crete, the day that the announcement was made. And we had a whole session devoted to that. This is how we measure its mass. It's much bigger than the colliding particles. And we were able, this is a demonstration that we can create a watermelon from the strawberries. And here are the scientific data from this discovery. I will go in the next 5-10 minutes till the end of my presentation to other 2 ways of looking and studying and trying to identify the Big Bang. Both of them are under development, so we cannot say that we have real data, that demonstrate that we can go so far. But in principle, we have the proof of concept. We have tried to get data that demonstrate that the principle is working. It's a very, very demanding process. Here you see a ship And there are some guys here, some researchers, who are looking to the bottom of the sea, and there they see the stars. Is it a bit crazy, eh? But here is another similar image. Researchers are opening holes in the ice, and they are looking there and they see the stars. In principle, this is how the process of neutrino telescopes are working. Neutrino telescopes, instead of using photons like conventional astronomy, are using neutrinos. The neutrinos have no charge, so they will not bend. They have very, very small mass. This was another Nobel Prize that rewarded some years ago related to that. And they have the unique characteristic that they can cross the mass like the light is crossing the window, the glass. So for them, the mass is transparent. From the moment I have started my talk, millions of neutrinos have crossed my body, and they have gone through the Earth to the other side of the planet. If we were able to see neutrinos, I will not be able to see you from the heavy rain of neutrinos that we are experiencing this moment. But we don't understand anything. So as we have so big number, and they are not interacting a lot with matter, it's very difficult to detect them. So there is a whole technique that we are going to discuss on Thursday on how these telescopes are working. Here I'm just going to make a short introduction. The neutrino is coming from the center of the planet, has crossed the planet. So that's why the guys on the ship or in the ice, they were looking to the other side, because the neutrino telescopes are located in the bottom of the sea, but they are looking to the other side of the planet. So we are looking, if we install a neutrino telescope here in Greece, in the ocean, we will look the sky of the Pacific Ocean, the sky of Hawaii, for example. So the neutrino is coming. Some of them, out of the millions of neutrinos that are coming, will interact with matter. It will give a muon, and the muon, when it's entering in the light, in the clean light or in the seawater, it will produce Cherenkov light. Why is doing that? Because the muon is moving faster than the light in the water. So we know that the highest speed is the speed of light, but this is in vacuum. When light is entering in the sea or in the water, it reduces its light, okay? Its speed. It reduces its speed. But the muon, moving with about 80% of the speed of light, is not going to reduce its speed. So the muon is keep traveling with 0.8 of the speed of light. And when this is happening, it's producing a blue light, a cone of blue light that is called Cherenkov radiation. And with the neutrino telescopes, we are installing these detectors at the bottom of the sea in order to be completely dark, to be able to detect this blue light. And we are able to reconstruct the track. And by reconstructing the track of the muon, we are reconstructing the track of the neutrino, and we are able to set targets in the sky. And we hope that these targets they are located much, much further away than the targets that are coming from light. One major effort took place in Peloponnese, at the southwest end of Peloponnese, at a depth of about 4,000 meters under the sea. And this is a different way of constructing telescopes. So here we are deploying a whole structure that has these optical modules, as we call them, sensors, that they are located there to see these blue light. This is one floor of a very big telescope, about 330 meters height, in order to see the light of the neutrino. So this is the construction. Here is a similar experiment, much more advanced, that is taking place at the South Pole in Antarctica. So you see, this is the size of the detector, and this is the size of the Eiffel Tower. And this is the upper part of the ice. In Antarctica, the ice is about 3,500 meters deep. They are opening holes with very hot water, up to 3 kilometers, and they are deploying these optical modules inside. This is the station at the South Pole, and this is an event. You see, all these optical modules waiting to see this blue light, and this was an event. This was announced in 2013. It was a very high energy particle. It had an energy of about 200 TeV, tera electron volt. It means it's 100 times, 200 times more energetic than the energy that we are able to give to the particles at LHC. So from where these kind of particles are coming from? They are coming from cosmic accelerators, like this one, okay? So in principle, we have demonstrated that we are able to detect neutrinos that are coming from these structures. And we hope that in the future we will develop much more advanced neutrino telescopes to see neutrinos that are able to escape the cosmic soup. And we are able to see neutrinos that they are coming from Big Bang. The third case is the observation of gravitational waves. As it was, this was discussed yesterday, so I'm not going to devote time to that. I will close just with one video. I just want to say that this is the fourth Nobel Prize that we are going to discuss in this summer school. We will have a lab exercise for you related to that in order to demonstrate. Just to remind you that 36 solar masses black hole collided with 29 solar masses black hole, and they created a 62 solar masses black hole. And this was the first event that was detected back in 2015. It was presented in 2016, and 3 solar masses of energy were released to the universe, creating these very big gravitational waves that we were able to detect. Again, as it was presented yesterday, this is a process under development, in progress, to develop bigger and bigger detectors to be able to see gravitational waves that are coming from Big Bang. Because also during the Big Bang, significant gravitational waves were created. I would like to close my presentation with a video that I think it's really a tribute to the scientific process.
Interferometer gravitational wave
from
observatory.
The key actors themselves,
LIGO
they are presenting
really
their effort.
Observatories that work in
I believe this is the message,
the LIGO interferometer
especially
has
for you,
that are about 2.5 miles long,
young people who have interest in the scientific process,
laser produces
to see how difficult it is in principle to turn a theoretical issue to real, and provide real experimental data for this.
40 kilograms, which is about 88 pounds. They're about this thick, and they're just the purest material you can imagine.
The NSF, of course, had to be the source of funding for anything that would be as expensive as this.
This is going to be a very high-risk experiment.
There is always the financing body that has to be convinced to support this effort.
In the 70s and 80s, I'm amazed at how bold it was to do this, and visionary. It was bold and visionary. There's no other way to describe it.
NSF management, the National Science Board, they had to really step up to that. And they had a lot of discussions, brought in a lot of experts. There was great debate going on. But in the end, the people who thought it could be done won the day, and they went after it.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1,000th the diameter of a proton.
Even Einstein himself never thought a detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of LIGO. What the gravitational wave does is it stretches space this way and compresses space that way. So you exploit that property.
Weiss is the second
one
person
object
that
here
received the
and
Nobel
another object
Prize,
over there,
and he
and let the
demonstrates
gravitational
how
wave go
simple
through that
ideas,
system,
basic
and it'll change
ideas,
the space
can
between
change
these by contracting that one
the
and extending that
process,
one.
The way
And I came to
that
the
we are
conclusion
thinking.
that if you make this long
we are
enough,
looking as
if you didn't make it a little
the director of
like
the
this, but you
American
made it sort
Farm
of
School
kilometer scale,
said
you could probably
yesterday,
get these
for
extremely
people who are
precise
going to
measurements.
ask the correct questions. This is what
Nobody had ever
the
made
answers
something
we
like
have
this before, so there was a lot of technological challenges that
the correct questions. We need the people who are going to think out of the box.
It was just amazing, mind-boggling.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
We have observed gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
Well, this is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.
So, thank you. Questions?
In the picture with...
Yeah, I'm going to do that.
There.
Nene.
It's left gravitational wave or a right gravitational wave? It's left from that or right from that?
What do you mean? The picture you said about the star, no?
Yeah.
This is not a gravitational wave. This is...
Yeah,
This is light. Here I'm speaking still for the conventional astronomy and the efforts we are making in order to see as far as we can. Okay? So, imagine this is the deep space. And this is the limit I can see. And suddenly, it's a natural phenomenon, natural phenomenon. It's not a technique. It has nothing to do with technology. Here, because of these galaxies, the light that is coming behind, maybe this star is behind these galaxies, so we will never be able to see it, but the light bends. So I'm able to see not only behind these galaxies, but also further away, because it's like putting a magnifying lens in my optical field. So I can see more clearly and further away. And then, again by chance, because it happened, this is the pictures of the galaxy. I'm not able really to see any star there, but there, because of the location of this star, I was able to see it. So this is not a gravitational wave. Gravitational wave is a completely different thing.
Yeah.
I need a completely different detector in order to see that. We will have a whole lab in the next days to see exactly how we are working. But this is light. This is light. Okay?
Yeah.
Perfect.
Thank you very much.
Yeah. Could there theoretically be an application of high-energy neutrinos in particle accelerators? And if that was possible, what results could that produce, theoretically?
You mean to produce neutrinos at a particle accelerator?
Yeah. No, I mean to, for example, we saw previously that high-energy neutrino was detected in Antarctica.
Yes.
And that could these neutrinos theoretically be used for particle accelerators? Because you said that it was, I think, about 100 times stronger than the force applied in particles in the Large Hadron Collider.
In principle, neutrinos are produced at accelerators.
Yes.
So also at CERN, it's a great source of neutrinos. By the way, there is a great experiment in Gran Sasso. So we are shooting neutrinos from CERN to Gran Sasso in Italy. So the principle is exactly this. The cosmic accelerators are producing neutrinos. Okay? So the issue is at CERN, we know exactly where the neutrinos are coming from. But with the cosmic accelerators, we are trying to create a completely different map of the sky and see the sources of neutrinos. With light, this is very easy because we know immediately that this is a source of light, another source, another source. With the neutrinos, we have to create a new map with the neutrino sources. Okay? And we expect that the higher neutrino, the most energetic sources will be the black holes. So in principle, if we put the two maps together and we have a map of the sky taken by telescopes, the more advanced telescopes, at the centers of the galaxies, we will see all the black holes. All the points that are missing in our conventional map will be filled in with a neutrino map.
Yes. Thank you very much.
Okay? This is the idea. This is, let's say, you mean these ones?
Yeah.
These are just some images. Usually these stars, these very big stars, have a companion star. Okay, so the idea is, this is not clear yet because this is very new data, that we are not only able to see the star, this very far star, but maybe we are able to see its companion. But this is still under investigation.
So those two are like less important than the main one?
Yep. Okay, so we have let's say 5 minutes break, and we can start with the next presentation. No. It's there is a small break now. Okay. And I'm here if there are further questions. More than happy to answer. I just want to say that for the neutrino telescopes, there is a whole session on Thursday. So we will explain the technique. And then there is also a workshop where we will introduce the photoelectric effect that is really combined with the technique of discovery of light that is coming from these detectors. And for the gravitational waves, we have again a lab exercise on Thursday and on Friday in order to get introduced in this detection technique.